Okay, good afternoon, ladies and gentlemen. Let's have another short session and finish for today. As I told you, now I'm just talking and you're listening there, maybe. But the most important thing here is, I think, your intention and the discipline. If you really want to learn, I mean, get some idea about what is this thing, right? Maybe you need to also watch a little bit more related videos on YouTube and practice a few questions. And of course, the best way to learn is in math. You need to solve some problems, the practice problems. As you practice more and more, number one, it gives you some, what is it, self-confidence. You just say yourself, oh, okay, now I got it. I can do that. I can make connections between things. And the most important thing is, if you cannot make connections between the concepts at the time, you may get lost there. Now we have actually simply, I mean, generally we actually, what is it? We have been studying about how to solve uh, system of linear equations. That's what we are doing here. And we have just developed some techniques. Not we actually, they developed some techniques and we are learning those methods, how to solve this in a more practical way and also in such a way that we can write an algorithm and just give it to the computer and computer does calculation for us. Now we will talk about the applications of linear system of linear equations. Actually, really, there are a lot of applications for the system of linear equations, right? And you have been studying about systems of linear equations since maybe grade 5 or grade 6 from your primary school or middle school. At the time, maybe it just gives you some kind of, what is it? You just go to the market and you buy, let's say, some chocolate cake and coffee. Let's say 3 chocolate cake and 5 cups of coffee, you pay this much. Next day, you actually buy, for example, 3 chocolate cake and get, let's say, 11 cups of coffee for a party, you pay this much. What is the individual price of these items and blah, blah, blah. Actually, from grade 5, actually, what is it? We introduce students with the idea of the simultaneous linear equations. Now we are just going to have a look at some of them, and also I will ask the questions. I mean, from this part, from only those that I have mentioned. Like I'm going to skip maybe 2-3 parts. It's optional. If you're really interested, you can. Otherwise, we cannot actually, how to say, uh, learn every detail of these things. Let's start with the first one, allocation of resources. Okay, the first example. A biologist has placed the 3 strains of bacteria denoted by 1, 2, and 3 in a test tube where they will feed on 3 different food sources, A, B, and C. So actually the strain means that here we have a kind of bacteria tube. Let's say this is tube A, where the second one is tube B, and the third one is tube 3, right? So this one is tube A and tube B and tube C, 3. So you have some kind of bacteria here, okay? You're just doing some kind of experiment. It says where they will feed on 3 different food sources, A, B, and C. The first one, we're just giving food A, food B, and food C. Each day is 2,300 units of A and 800 units of B and 1,500 units of C are placed in the test tube, and each bacterium consumes a certain number of units of each food per day. We don't know actually how much they're eating. How many bacteria of each strain can coexist in the test tube and consume all of the food? All right. Now, of course, first you need to look at the table that's given, okay, because this table is given. Here we have food A, food B, food C, bacteria strain A, and the strain or strain, it must be strain, right? It is, what is it? Place and tube where this one, food, this one, stain. This stain. Must be strain, I think. Yeah, this strain is not, stain is different, right? Okay, let me correct this quickly. Strain, strain, strain. It is. Okay. All right. So now let's look at the table. This table is given. Food A. All right, food A, bacteria 1, it just consumes 2 units of food A in one day. Bacteria 2, let's say there's 2 units of food A, 3, 4 units of food A. We can just food A, food B, food B, can just say that maybe there's water, some kind of food, and some kind of mineral or something, okay? Just to understand this. And how about food B? Bacteria A, strain A, it consumes 1 unit. Strain B, 2 units. Strain A, it doesn't eat this food B. And how about the third one? Food C, strain A, 1 unit. Strain 2, 3 units. And strain 3, it is 1 unit. The question is asking, what is asking here? The question is, let me just highlight this. The question is, how many bacteria of each strain can coexist, right? We can just put into the same tube, coexist, so that the test tube and consume all of the food, right? So now we assume that actually here, this X1 and X2 and X3, that is a number of bacteria strain A, I mean strain 1, strain 2, and strain 3, right? If you just put this here, as here on the first step, for example, if strain A eats 2 units of food A, right? If we have X1, how many units of strain A food A they eat? It is 2 times X1, right? Because here we have X1 bacteria and each one is 2 units. And how about the strain 2? It is 2 times X2 because we have X2 strain 2 bacteria. And how about strain 3? It is 4 units. And here we have X3. That's why here we have 4 times X3. So altogether in food A, how much is given? 2,300 units. In similar way for food B, X1 plus 2X equals 800, X1 plus 3, X2 plus X3, that's equal to 1,500. Now, as you see here, if we just model this problem, right, and we get something algebraic equation, that is, this algebraic equation is a system of linear equations, okay? And once again, guys, as I told you, okay, mainly here, we're talking about the method. It's not only about getting the answer, the method. How should we develop a method so that actually I can just give it to the computer calculate this for instantly, you know. So now we are going to use our method to solve this system. What we have to do here is first we have to form our augmented matrix. So our augmented matrix here is this 2 and 2 and 4. These are the coefficients, right? It is 2 to 4. On the right hand side, the constant term is 2,300. So here we have 2 to 4. And the second line is 1 to 0 and 1, 3, 1, 1,500. And next step, you know that, right? The next step is we have to reduce it to is reduced row echelon form. So by performing some elementary row operations, if you reduce this, we have this reduced row echelon form of this matrix. Actually, we did a few examples in the classroom. That's why I'm not going to show every step here, since we're talking about the application here, not the actual concept itself. Okay, so what does it mean? It means that right from here, if we actually put 100 bacteria of strain 1 and 350 bacteria of strain 2 and 350 bacteria of strain 3, if actually their eating rates are given as shown in the table, actually can just consume all of the food at the end of the day. Okay, that is how many bacteria? 100, 350, and the 350. Now, in another example, it says repeat example 1 using the data on daily consumption of food units per day. Assume this time that 1,500 units of A, 3,000 units of B, and 4,500 units of C are placed. Actually, here we're just adding the amount of food, right? Not the bacteria, because since we're talking about the same bacteria and their eating habits do not change immediately. So now this our food, right? Actually, what is it? We are using this table food one. I think it's different. Okay, it's different. All right, no problem. So now we are going to use again our system here. 1111, right? Bacteria strain A. Again, this strain, why this strain? Strain. Okay. So that's our system. And after that, we need to form our augmented matrix, right? That's the 1, 1, 1, 1, 2, 3, 1, 3, 5. That's a coefficient matrix. On the right-hand side, we have the constant column. And next step is, you know what to do. We have to reduce this to reduce row echelon form, right? So if you just reduce this to reduce row echelon form, we have these matrix. And after that, what are we going to do here? We have to solve the equivalent system. Is it solved here? No. So we have to solve it ourselves, I think, here. So now next step is we need to write the equivalent or corresponding system, right? So from here, x1 minus x3 is equal to 0. And the second row suggests that x2 plus 2x3, that's equal to 1,500. Okay. And since actually we need one, what is a free variable? This x3, it can be anything. So now from here, if I introduce that x3 is equal to, let's say, since we're talking about the bacteria, let me just label this by n. We know that this n is, what is it? Positive integer. It can be equal to 0. And since we're talking about the bacteria, suppose it's not equal to 0. At least we must have 1. So at the time we have this solution, right? X1 will be x3, that is n. And x2 will be 1,500 minus 2 times n, right? And how about x3? x3 is equal to n. And of course, we have restriction here, right? What is the restriction here? Actually, this number of bacteria, right? This n, it must be greater than or equal to 1. And also this 1,500 minus 2n, it must be greater than or equal to 1. If you solve this for this inequality, so this n will be less than or equal to 750. So n is, let me just write in this order. So n must be, what is it? Greater than or equal to n and less than or equal to 750. Okay, so depending on this, you can just actually make some adjustments and put bacteria into these tubes so that they can consume all the food. Okay. For example, let's say if n is equal to 10, at that time you have to put 10 x1 bacteria, 10 x3, but 1,480 x2 type, or the strain 2 type. So since we are talking about the bacteria, it must be actually a big number, maybe. Let's say if n is equal to 500, right? At the time n is equal to 500, x1 equals 500, x2 equals 500, and also x3 equals 500. We have a lot of different options here, not the only one way. Another application is, what is it? Balancing chemical equations. Okay. So when a chemical reaction occurs, certain molecules, we call the reactants, combine to form new molecules, the products. A balanced chemical equation is an algebra equation that gives the relative numbers of reactants and products in this reaction and has the same number of atoms of each type on the left and right-hand side. That is what we have studied in chemistry. I don't know how much you remember. Actually, usually when you're writing chemical reaction formula, we just use arrowhead, right? And what is the main thing that what we remember? The number of atoms, right, on the left must be equal to the number of atoms on the right. For example, if you remember, for example, the water, that's an easy one, right? 2 times hydrogen, 2 plus an oxygen, 2, right? So that produces, what is it? 1 molecule of water, that is 2 hydrogen, 2 oxygen 1, right? And see here, if we just count the number of hydrogen atoms on the left, here we have 2 times 2, we have 4 hydrogen atoms on the left. And also here we have 2 times hydrogen atoms, we have the same, right? And how about oxygen atoms on the left? We have 2 oxygen atoms on the left. Also here we have 2 times 0 oxygen atoms. That is the rule actually in forming chemical reactions, right? The atom must be the same, otherwise. Anyway, that's the rule in chemistry. So now, let's see this example. The combustion of ammonia, what is it, NH3, in oxygen produces nitrogen in water. Find a balanced chemical equation for this reaction. Okay, this is a little bit, what is it? The thing is given, and that means that if you, this combustion of ammonia NH3, that means that if you just, oh, you're given the equation here, so I don't have to. So this nitrogen ammonia, right, there's W molecules if you add to X molecules of oxygen too, right? And they produce, what is it? They produce nitrogen, that is nitrogen, and water, that's the water, right? Um, Again, you are computer science students, okay? We are not expecting to know in detail about this, but at least some basic things you should know. One or two examples, get some idea about the application. So now, if you just count the number of atoms on the left and on the right, here we have W times, what is it, N? 1, right? So this W on the right, we have Y times 2, it should equal to 2Y. And how about hydrogen? W times 3, it is 3W. On the right hand side, it is Z times 2, it is 2Z. And how about oxygen? On the left, X times 2, it is 2X. On the right, we have Z times 1, that is Z. So this actually, for this reaction to be balanced, right? Actually, it must satisfy this equation. The number of atoms of nitrogen, hydrogen, oxygen on the left and on the right, they must be equal to each other. So now from here, if you form our system, we get this system, right? W minus 2y equals 0, 3w minus 2z equals 0, 2x minus z equals 0. What is it? It is a homogeneous system. And next thing we have to do is we need to form our augmented matrix, right? So 1, 0 minus 2, 0, 3, 0, 0 minus 2, and 2, 0, 0, negative 1, 0. Anyway, so after forming this one, you know how to reduce this to reduce to echelon form. So if you do so, actually we'll get this matrix, okay? Now what is the next thing? Is so I mean this calculation part, actually I just wrote this to save some time. So after this step, right, after bringing this into reduced row echelon form, now we need to write the equivalent system. So the first one is, what is it? It is, so we have how many variables? This one is, what is it? W, this one is X, this one is Y, we have this Z, right? We have 4 variables in alphabetical order. So the first actual row suggests this equation, W minus 2 over 3 Z, that's equal to 0. And how about the second one? Y minus 1 over 2 Z is equal to 0. And the third one is Y minus 1 over 3 Z is equal to 0. Okay. So now you see here's 3 and 2 and 3. If I just actually, we have one free variable. If I introduce the Z as, what is it, 60. At that time, we can have this solution. So W and the X and Y and Z, we just write in vector form. What is W? W is 2 times 2, it is 4t. And how about Z? It is 3t. And how about Y? X, sorry, X, Y, it is over 2, that is also, sorry, W is 4t. The second one is X, right? It's not Y. W, X, Y, Z. Okay, X. 3t. Y is 2t. And how about Z? It is 60, right? And since they're just asking only one equal solution, you can just write, for example, if t is equal to 1, one of them will be, what is it? W is equal to 4, and the X will be 3, and Y will be 2, and what is it? Z will be 6. Okay. Another application is in network analysis. I want to just say network nowadays we use a lot, and you have an idea about this, right? Maybe internet network or traffic network, or I don't know, the people, or what is it, aeroplanes network, and blah, 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 there are things. So network consists of a finite number of nodes. We call this junctions or vertices, connected by a series of directed edges known as branes or arcs, as you see in the picture. Each branch, because it shows the flow, right? It's flowing in what direction, like for example, traffic flow, right? One way, for example, in what direction people are driving their vehicles to. So each branch will be labeled with a flow that represents the amount of some commodity. So this commodity, it may be, what is it? Internet, right? Or water, or some kind of fluid, or maybe air, or traffic, right? The number of people, aeroplanes, anyway, so that can flow along or through that branch in the indicated direction. The fundamental rule governing flow through a network is conservation of flow. What does it mean? It means that at each node, the flow in equals flow out, right? That is conservation of flow. That means that, for example, if we are talking about this kind of space, right? And if this one is entrance, right? And this one is exit, right? So it's simply saying that, for example, internet connection, right? What is it? Or people, okay? If 10 people enter this, for example, tunnel, right? And at the end, 10 people should leave. The people who enter this must be equal to the people who leave, right? And also the water, for example, if you're talking about the pipe, if the water is flowing, the amount of water it enters must be equal to the amount of water it exits, right? That is conservation of flow. And how about if you have two brands, it's like internet connection. Let's say we are receiving internet connection whose speed is, let's say, some amount, let's say 100 megabyte, right? If two people are using, the amount of internet that two people are using must be equal to the amount of internet or whatever, or data, right, that is coming from outside. So these are just examples for flow. As you see here in the first one, F2 is flowing in this direction, F1 in this direction, F4 also to the right, and F3 towards this intersection point. Now it says describe the possible flows through the network of water pipes shown in the figure below. Okay. So let's see here. Now this A, B, and C, D, we have four nodes here. And from here, right, for example, if you look at the node A, the 5 plus 10 should be equal to F1 plus F4, right? And the node B, F1, right, should be equal to F2 plus 10. And how about D, 20 plus F4 should be equal to F3. And how about at node C, F2 plus F3 should be equal to, what is it, 5 plus 30. So now if you just write this in equations, the first one, 15 equals F1 plus F4, F1 is equal to F2 plus 10, and F2 plus F3 plus 5 equals 30, and F4 plus 20 equals F3. So what is it again? You just see that a system of linear equations, right? If you just simplify and write them in a more, better order, so you get this equation, F1 plus F4 equals 15, F1 minus F2 equals 10, F2 plus F3 equals 25, and F3 minus F4. Right. This is how we are describing this. Then if they ask a question, then we can solve this. How? By first writing our augmented matrix, right? And bring this into, or reduce this to a reduced to echelon form. And after we can determine the values of F1, F2, F3, and F4. Now, if you look at this one, right? Again, if you just write the equation, the last one is F1 plus F4, right? F4, that's equal to 15. The second one is F2 plus F4, that's equal to 5. And the third one is F3 minus F4, that's equal to 20. As see here, because we have 1 0 row, which means that the rank of this matrix is less than 4. It has actually one free variables, right? So that's why if I just introduce this one, F4 is equal to T, now we can actually, maybe I can introduce here, F4 is equal to T, right? Now I can write our equations here. F1 equals 15 minus T, and F2 is equal to 5 minus T, and F3 is equal to 20 plus T. And how about F4? F4 is equal to T. And since we are talking about the flow, we know that T is greater than or equal to 0. And now we can actually simplify this domain much further, because 15 minus T should be greater or equal to 0. That means that T here should be less than or equal to 15. Otherwise, it will be negative. Here, 5 minus t, so t should be less than or equal to 5. And how about 20 plus t? It is t is greater than or equal to 0. And also this one, t is greater than or equal to 0. So dot, 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 the final one is, what is it? T is greater than or equal to 0, right? And less than or equal to 5. These are the possible values for t. All right, guys, I think I will stop here. We have this current about physics, you can skip, okay? And also about this economics, what is it? Linear economic model, skip, you are not, it's optional. But we have only one linear system we have to study. Maybe we can do this in the classroom, or I'll share the recorded video with you, the last part, okay, this linear system. It's really interesting. Now I have to stop and we can continue in the class. Next week, as you know, we have class. Maybe we can have a bit more. Let's see. Next week we'll have class from 1 to 3 for everybody. Okay. See you next week. Bye bye.